Right, in the last lecture, we stopped at this graph. Can you settle down quickly? I was about to show you the simulations to illustrate the G field strength of two masses. Alright, so I'm going to go to that now. Okay, on the left, this is mass 1, on the right, this is mass 2. I have adjusted the masses to be 300 kg each. The red color dot here is a test mass with 1 kg mass. Can you all behave yourself? Okay, you can see that there are two arrows on the test mass. The pink color arrow is the force acting on the test mass by mass 1. Okay, and the light green arrow is due to mass 2. So if I move the test mass around, you can see that the length of the arrow changes. As I move it nearer to mass 1, the arrow gets longer, indicating that the force due to mass 1 increases. On the other hand, the other arrow gets shorter and shorter. Right? So the reverse happens when I move it nearer to mass 2. If I put it right in the middle, the two arrows will have the same length, they cancel out. So this is what we call what is the name for this point? Start with N. Neutral point, good. So now, for the next graph, the question is, what happens if one of the mass is higher than the other one? So now I'm going to show you the G field graph. It looks like this. The formula, one side. I told you to ignore the straight line. Okay, because this will be discussed in tutorial. Just focus on the curve. Focus on the curve. You can see that the G field graph cuts the horizontal axis right smack in the middle, indicating that this is G field equal to 0. What happens if I increase the mass of M1? So from 300 kg, I'm going to pull it up to 900 kg. So you can see that when M1 increases its mass, the G field graph gets further away from the center, right? Because the bigger the mass, the stronger the field. So the G field value increases. It pushes the graph up. And what happens to the neutral point? Is it still in the middle? It can't be, At the middle now, the force due to M1 is much greater than the force due to M2. The neutral point has shifted to somewhere here, right? Here. Closer to M2, the smaller mass. Okay, I hope you're not surprised by this. So back to your graph. How should you draw this graph? The one with the bigger mass should have G field graph further away, spread out further from the center. The one with the smaller mass, the graph should be closer to the center. And as a result, the net G field between M1 and M2 will be as shown. The neutral point will now shift toward M2. Okay, so this is our new neutral point. An example of this will be, for example, Earth and Moon. Earth is heavier than Moon, so the neutral point between Earth and Moon will be closer to Moon. Alright, please take it down. It's on. It's on. Okay, are we ready? We're going to solve some examples now. The first one is quite basic, so please try it. Look at it, read it, and try it. Okay, example 6. Application of G field strength of one body. First, understand the question. The astronaut is standing on the surface of a planet. It drops a rock from a height of 100 meters. It takes 8.06 seconds to hit the ground. What would be the acceleration due to gravity? How would you solve this? You are given the height of 4. You are given the time of 4. You need to find A. So basically this question got to be solved using kinematics equation. So we can use S equals to ut plus half at squared. We are given S, 100 meter. So we take down as positive, going down 100 meters. Timing is given. Initial velocity should be 0. So very easy, put in everything, calculate the A is found. 3.08 meter per second squared. Is this planet Earth? No, you can see from this it's not planet Earth. The G, the acceleration due to gravity is much lower than 9.1. 3 times smaller. Okay, go on to B. Go on to B. What is the mass of the planet? How do you find the mass of the planet? Using this information, A. How do you find the mass of the planet? So you can make use of the fact that the gravitational force acting on the rock equals ma, right? Okay, the gravitational force pulling the rock down by the planet is equals to ma. Plug in the value gmm over r squared equals to ma. What is this big M? Big M represents the mass of the What do you think is this big M? Mass of the planet or mass of the rock? What is this small m? Rock, right? Mass of the rock. So this must be mass of the rock, right? Small m. So this must be mass of the planet. Very good. Okay, so that means we can cancel with the mass of the rock because we don't know what is the mass of the rock. Okay, and we know A from part A. Okay, so the separation, we can just use the radius of the planet. If you want your answer to be more precise, by right, if you do something to this R value, this is the radius of the planet. Is it very accurate to say that I'm using this as using this value? Where is the rock? Is the separation between the rock and the center of the planet equal to the radius of the planet? What should I do with this actually? I should add another. I should add another 100, right? 100 meters to this. But this number is so big compared to 100, so the effect is negligible. You don't see the effect. The answer, no change the answer. And then so by right, you should add 100 here. Okay? Why you add 100? To the add 100 by right. Do you know why this power is to the power of 5? The value there is power of 2. How about this power of 5? Because of the kilometers, right? Kilometers. So very important, kilometers. Don't read wrongly during exam. Read carefully. Kilometers, you must add another 3, power of 3. So the answer is this, the mass of the planet. You know how careless you are, right? Right, you look at the semester exam, so many careless mistakes. You have to be more careful, a lot of you get getting A's. Okay, next part. Try the next part. What do you think will be the G field strength 50 kilometers from its surface? This is really far, 50 km away from the surface. So the formula is Gm over R squared. That will help us find the G field strength. You have found the mass of the planet, you can plug it in. But the question is, what is R value? What is R value? Radius of the planet plus 50. You plus 50 wrong already. 50,000. 50,000 because it's 50 kilometers. Okay, you need to add 50,000 meters to the R value, to the radius of the planet, then you get the R value. And the answer is this. Okay, so it's a very simple example getting used to the formula. This kind of question hardly come out in exam. If you see this kind of exam question, it's very happy inside your heart. You should be cheering. If you have any question, feel free to raise your hand. The tutors can help to help, or you can just shout the question if you don't mind. Can some teachers help to? I think the lights are not fully switched on. Can you help me to switch on, like partially on? A bit dark at the back. Okay, are you done with this? Okay, I have received insider info. This answer is wrong. Anybody wrong answer? It should be 10 to the power 22. 3 power 22. Thank you to those who calculated correctly. Okay, it should be 22. Thank you very much. Okay, next example 7. We're looking at this diagram again, Earth and Moon. So now what is the net G-field strength at the midpoint between Earth and Moon? So we're now looking at the middle between Earth and Moon. Okay, which is here. Is this a neutral point? No. Okay. So which field strength should be higher? Due to Earth or Moon? Earth. So the Earth's arrow should be longer than the G-field arrow of the Moon. As a result, what is the direction of the next G-field? Towards Earth. Very good. So instead of saying to the left, a better answer is towards Earth. So how do you find this net G-field? Very simple. Find G-field of Earth minus G-field of Moon, right? Okay, why minus? Because they are pointing in opposite direction. And I'm taking to the left as positive, right? So I take the positive to the left minus the G-field to the right. Okay, so I plug in the formula Gm over R squared. So now the key thing is, you must be careful. When you key in the M, which M? Okay, G-field due to Earth, use the mass of Earth. G-field due to Moon, use the mass of Moon. Common sense, please. But the next thing, what is R? What is this R? Separation. Is it 3.8, 10 to the power 8? Do I put this here? What is this R? It is from the center of the Earth to the point that you're looking at, right? So it should be half of 3.8, 10 to the power 8. Same thing for the other R value, due to the Moon. It is actually the distance from the point to the center of Moon for this R. Okay? Please get your basic right. Otherwise, later on, as you go on, you get more and more confused. If you are now confused, please ask a friend or ask a tutor. Don't pretend to know. Okay, I saved you the trouble. I calculated. Hopefully it's correct this time. This is the answer. The unit will be Newton per kg. And if I ask you what is the direction, you will say pointing towards the center of the Earth. Okay, those are ready. Can you go on to the next part? So what is the force acting on the space capsule? What is the gravitational force acting on the space capsule when it's at the midpoint? You have found the G-field strength at the midpoint. How do you find the force of the space capsule at the midpoint? Okay, so you already found the G-field strength, right? Net G-field at the midpoint. So to find the force, very simple, just take the G-field strength, multiply by the mass. Because you have found G-field strength, which is the force per kg, now you just need to multiply by the mass of the space capsule. And this is the answer. This is the force per unit mass. So far so good? Okay. You want Kahoot time? Okay, just want to do a quick Kahoot to just round up this section before we go on to the next part. You can take out your handphone, Google Kahoot, and then I'll give you the code now. For this force, the direction is also towards the center of the earth. Please take note of this. Okay, let's go. Again, no offensive nickname. Okay, I know you know the teachers go to our defense. You got a code? This is a code quickly again. I don't want to look at all the nickname. The code is 8559153. Okay, give me another 10 seconds. I'm going to start. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay, let's start. Half of you are in. Okay, 3 questions. First one. Ready to start. Don't look at your lecture notes. I forgot to tell you the winner has a prize today. We have a prize today. Okay. Okay, the answer should be gravitational force per unit mass. Per unit mass. Okay, that's the definition of G field strength. Okay, please read out, 47 of you. Okay, District 69. Good job. Next question. What is not true? What is not true? 5, 4, 3, 2. Ah, very good. You are listening. So G is not always less than 1. It is only equal to less than 1 and the surface of Earth. Why? Okay, let's go on. Don't know what is this. The wheel. Last question. What is true about neutral points? Wow. What is this? Okay, reteach. Okay, let's look at the score. Oops, I've lost connection. No, I got it. Okay, we have a champion over here. Actually, we have 2. Who is this? T. God be the glory. Sui Bian. Okay, you can come and collect your gift later. Okay. Let's round out the section on force and field strength. Okay, in gravitation, you have finished mastering the field strength and force. Basically, force and field strength are vectors. Okay, field strength is basically just force per unit mass. I'm going to move on to the next section, energy. This is a part that is going to be quite confusing because GPE has a totally different meaning now. Very different from work, energy, power topic. Okay, what is gravitational potential energy? Please focus your attention. In topic 5, when you learn about energy power, you use GP equals mgh. For example, if a 5 kg mass is placed at a certain height from a reference level, okay, let's call the reference as 0 meters and the height is 10 meters. The GP of this 5 kg object can be found using MGH. So we calculate the MGH to get the value 491 joules, right? This is simple. But why are we using this reference level? What happens if the reference level is not here, but somewhere here? Then the height from the reference level will be different, right? For instance, when I stand on the stage, if you take the stage as the reference level, I have no GP. But if you take the ground here as the reference level, I have no GP, right? So which reference level is the correct reference level? So if I look at this new reference level, I use MGH again to calculate. My height should be 15 meters, I will end up with 736 joules. Which is the correct GP? It cannot be like you decide, the reference I decide, you decide, and everybody will give an answer, right? So what is the actual GP? So the truth is, MGH does not give you the GP. Then what does MGH give you? It gives you the change in the GP. Okay, when the object moves down 10 meters, what is the change in its GP? At the same time, this formula MGH uses G as 9.1. 9.1 is only true when you are at the Earth's surface, right? What happens if I launch you all the way 100 kilometers up? Then your GP cannot be using MGH because your G is not 9.1 anymore, you understand? The G will have changed and you go further away from Earth. Okay, so this will illustrate near Earth's surface uniform 9.1, but then further away from Earth it's not. That's why in this chapter you're going to learn the absolute, the true value of GP. Okay? And we need to do that because GP strength is not constant when we talk about very large distances, separation, and the reference levels should be consistent. I heard someone saying, let the reference level be the center of Earth. Then people say at the Mars will be complaining, why Earth? Why Jupiter? Why not Jupiter? Why not Sun? The Sun heavier than Earth. Shouldn't Sun dominate? Then how about so what? Okay, so now we're going to look at GPE as the true meaning of GPE. We're going to use a new symbol to represent GPE now. We call it capital U. When you see capital U, it represents the true GPE. So I was telling you Earth and Mars. Okay? If we use the surface of Earth as reference, question is why? Why not Mars? Use the center of Earth? It's not fair. Surface of Mars? Okay, so the scientists decided that we're not going to use any planet. We're going to use a universal reference. Where is it? It's not the center of any planet. We're going to use infinity. Infinity is a conceptual word, right? Where's infinity? Very, very far. How far? Very far. How? No, just very, very far. It's a conceptual word. It's just very far. So far that nobody has ever reached there. Infinity. And we call it the reference level at infinity. And the funny thing is, if I plot infinity as my reference level, infinity becomes 0. Isn't it? Sorry. Infinity becomes 0 joules. Okay, so I'm going to explain a bit more later on. To help you understand, let's recap what you learned in work energy power. I have an object, the hand is holding on to the object. Okay? The hand needs to push the object up in order to keep it there. If I'm going to raise the object up, okay, the force will travel upwards, the displacement will go up. In this case, the force acting on the object and the displacement, they are in the same direction. The work done is positive. Positive work done on the object will cause the energy to increase. You are increasing its GP, right? Okay, understand? What happens if you place the object down? You still need to push it out, right? Or do you like push it out? You got to just still hold to it, but now you lower it down. So the force exerted is up, but the displacement is down. So in this case, the work done is negative. Negative work causes energy to drop. That's why you bring something down, it reduces its GP, isn't it? So far so good? Okay, what happens if you bring the object until infinity? Very high up, all the way to infinity. Are you doing positive work? When you raise it up, you gain energy, the object will gain energy. You gain a lot of energy, right? Keep gaining energy, all the way to infinity. So what happens to the GP and infinity? Very high or very low? You keep bringing it up, it should be very high, right? So the infinity and infinity, the GP should be the maximum, but the scientist point is 0. Because there's no way to give a number. How do you give a number? 1 million, 3 million, 50 million? Right, there's always a number bigger than the number that you state. So the point is 0. So now the basic thing is, the maximum potential energy infinity is 0. If the 0 is infinity, anything lower than infinity will not be negative. That's why GPE value, the true GPE value, is always negative. 0 and infinity, anything lower than infinity is negative. The more you go down, the more negative. The more negative, the more negative. Understand? So this is the concept of GPE in topic 7. So let's say if I bring it down to this level will have an energy less than infinity energy, which is 0. Therefore, this level will have a negative U. Okay, just get this idea in your head. I'm trying to brainwash you. Okay, get used to this idea. Okay, so how are we going to calculate GPE from now on? It has to be negative, right? It has to be negative. So we have a formula for this. So this formula shows that if you want to find U, we use negative GMM over R. What is MM? Two masses. If there are two masses separated by a distance R, the potential energy of these two masses is equal to this. Negative GMM over R. Okay, please take note, this is not R square, it's not R square, you don't confuse with the gravitational force. Energy only has one R at the denominator, 1R. Next thing, be careful, it's always negative. Don't forget to put it negative. Some of you are very allergic to negative. In your exam working, I see negative, not negative, but yes, negative. Don't know how, just cancel it. Okay? Potential energy will always be negative. Okay, I'm going to explain how come this formula makes sense for this new idea of GPE. First thing, GPE is a scalar quantity, it's an energy, it has no direction. Please remember this, energy has no direction. When we say that the GPE is negative, it is not pointing in the negative direction, it is just less than 0. Just less than 0. Next thing. U is always negative. Based on the formula, it is negative. But what happens when R changes? So let's illustrate using Earth. Earth and a point mass over there, separation of R. If I move the point mass to this point, let's say the U is minus 100 joules. Okay? As R increases, if I move it further, what happens to the R? You look at the formula where R increases, GMM over R will drop, right? GMM over R will drop. You end up with a smaller GMM over R, but because of the negative sign, a negative small number becomes a big value. So this part a bit confusing. This 100 becomes 50, but then it's a negative 50. So this negative 50 is actually greater than negative 100. Get it? So the GP actually increases. So if you keep increasing R, you actually have a bigger GP value. Yeah, I'm going to give you some time to digest this. See whether you digest it. If you're confused, you can talk to your friend. Look at the formula, let me send for the formula. What happens when R increases? You okay? Now it's time for growth mindset. You face the challenge, don't give up. You keep trying. Okay, for those already, look at this. What happens when R becomes infinity? If R increases to infinity, this whole value becomes 0, right? Which is 0, correct? We just said that U is equal to 0 infinity. So this formula is really helping us to determine the U value. Okay, I'm going to move on. Okay, focus your attention please. Okay. Another way of doing this, if you really have a question, you can use a pencil pen down next to your notes. Okay, later you can ask the tutor. Okay, next part. I will say that when R becomes infinity, U becomes 0, right? So this is aligned with what we were saying just now. And take note that this infinity is our reference level. It has 0 U, 0 joules, but it's not the minimum, it's actually the maximum. Maximum. If you want to understand how this formula is derived, how come you use this formula? You can refer to the appendix A. Do you need to know it for exam? Answer is okay. You won't test you. But if you are very curious, it's your appendix A. If you're not curious, then write the formula. Okay. You have learned the formula. Next thing is the definition. So now how do you define TP? If it's always negative, how do you define TP? So the definition is like this. Also very out of the world one. The definition is, it is the work done to bring the mass from infinity to that point. I can sense that 50% of you are giving out already. Can you raise yourself up and come on. Focus your attention. Definition of infinity is work done to bring the point mass from infinity to that point. What is that point? That point is whichever point you place the point mass on. Okay? I'm going to illustrate using this. So carefully, if this point is at infinity itself, then I will be looking at what's done in bringing the point mass from infinity to infinity, right? If that point that I'm bringing is infinity, then the work done to bring it from infinity is to be equal to 0. Because in the infinity, there's no need to do any work. Okay, next one. What happens if the point is here? Then what this definition is telling me is the GPE at that point is actually the work done to bring this point mass from infinity here to this point. Okay, so it takes negative 50 joules to bring the point mass from infinity to this point. But the question is, why negative 50? Why is the work done negative? Why is the work done negative 50? Think. Okay, this is to explain why it's negative. When we talk about bringing the point mass from infinity to that point, where the point is here, you can draw this in. Just pick a point. When you talk about work done from infinity to this point, you have to take note that the external force. Oh yeah, my sequence is a bit messy today. I need to draw that point first, whatever that point is, and then label this as R. This is the separation between that point and the center of the soft mass. Okay, then you will draw this in, because you are moving the point mass from infinity to that point, so I draw in this displacement direction. Okay? Ready? Okay, so now, when you want to bring the point mass from infinity to that point, you are talking about work done by an external force. External force, not the gravitational force. So please think of this. What is the direction of this external force? Okay, this is what we're going to do. This is the object, right? And infinity. Okay? if I let go of the object, the planet there is going to attract it, right? So the gravitational force is going to pull it towards it, right? Okay, so if I let go, it goes, right? So now, if I want to bring this object from infinity to that point, not to the surface but to that point, what should I do? If I let go, it will go, it will get attracted. So I need to pull it back. So the external force that I need to apply is actually away from the planet. So that you will go against the gravitational force of the planet and then hold on until it stops here. If you don't exert the force this way, it's not going to stop here. That gravitational force will pull it all the way. You get it? So the external force is actually pointing away from the top planet. And because of this, look at the force direction and the displacement direction. Then think about the work done. Okay, we'll draw all this in now. Okay, all this is just describing what I just said. Don't repeat it. Okay, so is the work done positive or negative as you move from infinity to that point? So F is to the right, S to the left, the work done should be a negative work, right? Why is it negative work? Because F and S are in opposite direction, right? Okay, write it down so you can remember. So what happens to the U, which is GP of the point mass, as a result of this work done? When you move from here to that point, you are doing negative work. What happens to the U? The U will decrease. You get smaller because you are doing negative work. Okay? So now can you explain why we are having a negative sign in this formula? After looking at this question has come up many times. Why is GP always negative? Why is the formula having a negative sign? Then you explain by saying, because we take the U at infinity to 0, okay, and now the work done by this force is negative. Therefore, U will end up to be negative. We start off with saying U is 0, and this is a negative work. Of course, the U at this point will be negative. Okay, so this is a very short way of answering it. If you are not very clear about the answer, you can add in, you can expand the answer, make sure that you know what you're writing. I know what I'm writing here, but I'm not sure about you. If you don't understand, you write it more. Okay, if any question you can stay back and ask me later, no problem. Okay, one more question, right? Do you think that the force acting on this point mass is constant throughout? Do you think that the external force exerted on the point mass is constant throughout? The answer is no. You can't finish that. Wow. Can you hurry up? Thank you. Anyone say copy? Okay, let's move on. Do you think the magnitude of the external force is constant as it moves from infinity to that point? The answer is no. Why not? As you move closer and closer, what happens to the gravitational force? Increases. So this external force also has to increase to counter that gravitational force. If you plot the gravitational force versus distance graph, you will look something like this. So you can see that the force gets stronger and stronger when it's getting nearer to the mass. Anyone can explain how come the graph is negative? Why is this force graph as well as the negative side? Because anyone say that because energy is negative? This is not energy, this is force. Why is force negative here? Because it's pointing towards the gravitational force on this side is pointing to the left. You put any object here, it will pull towards the left, right? So the force is to the left. That's why it's negative. Get it? Confused? Look at your GP graph. Your GP graph, they have one positive, one negative. Okay, so if I put infinity at this point, it's almost zero. That point, somewhere here, you can see that the force actually increases in magnitude. The negative side is only about the direction, not the magnitude. I'm going to try and test water, see whether you can stretch it further. What do you think is the area under the ground? What is that? Work done. Force, distance graph, area under the ground is work done. And that's not what we say about GB. It is the work done to move the object from infinity to that point, right? So this area is actually the work done to bring it from infinity to that point, meaning this area is actually the GP. This is actually the potential energy at that point. Okay, this one is a bit cheap, huh? Okay, I need to go back and digest now. Really, it's not easy. Okay. One more minute. Yeah, okay. So I think I want to go on because I think we're not finished. Okay. I'm going to just go over here because it's really not easy. Go back and read out. Okay. I really think because of this part, if you don't read out, it's really confused. I'll see you next Monday. Read out the notes. Write examples if you can. Right? Class list. Can I have the class list back?